So let's think about second order systems. In fact, in particular, we're going to think about their responses. Now, a second order system can be described using a second order differential equation. So that would typically be of this kind of form: a d squared x dt squared plus b dx dt plus c x equals some driving force f of t. Now we're going to think about these things using Laplace transforms and consider them in the S domain. So we can take Laplace transforms of both sides of this, and we're just going to worry about transfer functions in the first instance, so we shan't worry about initial conditions. So we can see that the a dx squared dt squared goes to a s squared capital X of s, the b dx dt goes to bs capital X of s, and the cx goes to cx of s. And of course, f of t goes to capital F of s. We can factor out the x of s quite easily. And then what we need is to know what is going to be the transfer function. So what's x of s divided by f of s? And we see quite easily that just goes to 1 divided by a of s plus b of s plus c. Now what we're going to do is we're going to write this in canonical form. And this is a way of writing a second order system in a way where the coefficients have got an important meaning. So we're not going to worry too much about the numerator, because the numerator depends a bit on the system you're doing and analysing, or it can do. It's really the denominator that we're really interested in here. So what we're going to say is we're going to write it in a way that there's no, first of all, no coefficient in front of the s squared term, right? There's going to be unity there. The s term is going to be written in terms of 2 zeta omega n, and the constant term in terms of omega n squared. Now, the zeta and the omega n have got special meanings. Omega n is going to be the natural frequency of the system. It would be the frequency at which it oscillates at if it wasn't damped. And the zeta is going to be the damping ratio. So how damped is this thing? And if it wasn't damped at all, it would be 0, right? Now, obviously, we want to think about how to understand, what this transfer function means in terms of the behaviour of the system, and we know that the poles of the system tell us a lot about this. So we can first of all look at this expression and say, well, we care about where the poles are on this system by looking at the denominator, and we know that when the denominator goes to 0, the values of s correspond to the poles. So we can write the equation down telling us how we, when the poles occur, and it's when the denominator term s squared plus 2 zeta omega ns plus omega n squared equals 0. Now this is just a quadratic expression, so we can use the quadratic formula in order to solve this. So as we all know, or we should know by now, ax squared plus bx plus c equals 0 has got the solution for x in this case. X equals minus b plus or minus b squared minus 4ac divided by 2a. And we also know that if the term in the square root is such that the b squared is bigger than 4ac, we'll have a real solution. But if the b squared is less than 4ac, we're going to end up with an imaginary solution to that part of the equation. Right? So we'll end up with an imaginary number creeping in there. So let's look at our s squared plus 2 zeta omega ns plus omega n squared equals 0. We'll use the quadratic formula in order to solve this. So we just put in the b as the 2 zeta omega n. That's here. That goes in here, b squared minus 4 times ac. So a is 1 times c is omega n squared divided by 2a, so divided by 2. Then we can just go through multiplying. We multiply it first of all with the squared term there. And then we take out the factor of 2 omega n from the square root term. We divide through by 2, and we end up with a fairly simple expression for s. So s equals minus zeta omega n plus or minus omega n square root of zeta squared minus 1. And if zeta squared minus is less than minus 1, obviously we're going to get a complex result overall, in which case we can flip the order of the complex, of the square root term, and instead we put a j in front of the solution because it's going to be an imaginary component. Now, the response of the system is going to be very dependent on what the values of the zeta is and the omega n are. So we can go through, we can look at this equation and we can say, well, what's going to happen when the damping ratio zeta takes different values? And when zeta is bigger than 1, first of all, we say the system is going to be overdamped because it's got a lot of damping. And we end up with an expression which looks like this, the solution. And this is basically the solution with a real solution, right? So we've got S equals minus zeta omega n plus or minus omega n square root zeta squared minus 1. When zeta equals 1, then we get an interesting effect because what happened in this square root before is now basically it goes to 0, right? So we end up losing that term altogether, and S equals minus zeta omega n. In fact, this damping, basically what it's done is it's made sure that the system is still non-oscillatory, right? We've got no complex parts in this solution at all, but the zeta is as big as it can be without actually being overdamped. That's the important thing, and this is actually known as critical damping. Now, another interesting condition is when the zeta is between 0 and 1, in which case there's not as much damping as critical damping, and we'd call this underdamped, right? So in the underdamped condition, then we actually have a complex solution coming in now because the 1 is bigger than the zeta squared is actually less than 1 now. So this term leads to an imaginary solution, so we can put the j in front of it. So what we see in this particular case is we've got a real part which is negative, so the system's going to be stable, but we've also got this imaginary part, which means oscillations, if you recall from poles. So poles with imaginary parts, there's something oscillating in there. Now, if zeta is 0, then what we find is the initial, the term at the front here, this bit here, disappears, and we have a purely imaginary solution, which means it's going to be completely oscillatory at a constant amplitude. And if zeta is less than 0, then what we find now is we have this term used to be negative, but now it's gone positive. Therefore, we're going to end up with an unstable system. So we're going to have a system which has poles with a positive real component. Then off it's going to go, if we're not careful, into oscillations that are increasing. So just to summarise then, if zeta is 1 or more, then we've got a stable solution that's just decaying exponentially. If we've got zeta between 0 and 1, it's still stable, but it's going to oscillate. So we've got this oscillatory decaying exponential envelope on our sine wave. If there's no damping at all, it's just oscillating forever. It'd be like a perfect pendulum that you let go. This basically goes backwards and forwards. It's not damped, so it carries on with the same amplitude forever. And that would be marginally stable. And if we have less than 0 damping ratio, then we've got unlimited growth, so we've got an unstable system. We can plot out by doing, this is actually running a simulation in Matlab. I shan't go through how I did it, but basically this is kind of what those situations look like. Let's start at the bottom with the blue one. The blue one is overdamped, and this is having a system and driving it with a step. So the ideal response of this will just be going up to 1 and carrying on, just like a step. In this case, we're driving it. If we do it with overdamped, we see that we get this blue curve coming up slowly, and if we wait forever, it would actually get there. So it's coming up very sluggishly. Critically damping is when we go up as fast as we can without any imaginary part to the pole. So in other words, it's rising up as fast as it can without in any way being oscillatory. It's not going to overshoot. It's getting high. It goes up as fast as it can without anything being oscillatory. So there's no overshoot in that condition. That is in contrast when we actually go below 1 for the damping ratio. So if we go to 0.5, we end up on this yellow curve. So it's now got this oscillatory component, so it can start oscillating up and down. And in this case, it does overshoot, but not very much, and then it comes basically down quite quickly. And if there's no damping, what we'll end up with is a continuous oscillation forever. Right. We can also do an analytical version of that. That was just basically simulating it in Matlab. The way we calculate the output from a step is we say, let's take the transfer function and multiply it by the Laplace transform for a step, which is 1 over s. So we multiply 1 over s with our transfer function, and we end up with a solution. You can then transfer that back to the time domain using partial fraction expansions and inverse Laplace, and it's a pretty horrendous thing to do, but it's quite informative to look at the formula, right? So the formula looks like this, and this tells you quite a lot about the properties of a second order system as a function of omega n and zeta, right? And what we see, right, is the oscillatory frequency, right, is actually damped. It's not just the omega n, it's actually oscillating, but it's slightly pulled off what the natural frequency would be by the damping, right? It's slightly perturbed by the fact that it's damped. And that's the damped oscillatory frequency. We see that we've got a decaying term in front of the sine wave, or it could also be an increasing term if we had a negative zeta. Relating to, in this case, there's a time constant on that given by zeta omega n. Within the damped oscillatory frequency part, we see that there is a natural frequency component, but this is affected, of course, effectively scaled by this 1 minus zeta squared, which is then square rooted. Right? And there's a damping factor at the bottom as well. If we wish, we can also run an analytical way of simulating this system in Matlab. You can easily do that by multiplying, well, basically implementing that function, and you can do that, and you can simulate using this function what things will look like. Right. As a final note, it's good to know what basic times are relating to the responses, and there are a few important things that we can actually you should actually know about by looking at the waveforms of the responses, and one of them is the rise time. Right? So the rise time is the time it takes for the output of your system when you give it a step input. How long does it take to go from 10% to 90% of the value you're actually aiming for? And this plotted example, of course, is actually for an overshoot condition. So this is an underdamped system, otherwise it wouldn't overshoot. But you could do it also for a highly damped system. It would just rise up and rise up and rise up, and you'd want to know what the rise time was for that, and it would be a lot longer than it is for this underdamped system. The peak time is, again, really only mainly relevant if you've got some kind of overshoot, and it's the time it takes to get to the peak value. And it's also related, if you look at the equation that we've got, it's related to half the cycle of the oscillation. So it's related to this omega n square root 1 minus zeta squared square rooted term, right? So it's related to that term. We've got to change the angular frequency to the actual frequency in hertz, and then of course then we can also flip it up and actually get then the time out as well, in order to get half the period, if you like, of that, in order to give you the time. I'm not expecting you ever to learn these formulas, or it's a bit tricky, but it's good. You definitely need to be able to say, looking at that waveform, what's the peak time? In fact, you need to say what's the peak time, what's the rise time, what's the settle time. Peak overshoot is how much it's more than the than the goal. How much has it gone up by? So it's like that little bit extra from where it should have gone to, and it occurs at the peak time, of course. And it's related, of course. It's related to how this scaling factor. In fact, there's the exponential scaling factor divided by this term due to the 1 divided by 1 minus zeta squared square root thing affects the signal. So the scaling factor is given by this expression here. Okay, and that's very important that you to put. But again, you would not be expected to remember these things. It's just so that you can actually calculate them. You'd be given them as formulas. So in order to get this overshoot, obviously you've got to then put in what the time is here, and the time is the maximum, is the peak time. So you put the peak time into this expression, and you end up with what the peak overshoot is. Settling time, again, it's quite an important measure. It's basically how long does it take for the output. If it could overshoot, it could just be going up very slowly, but how long does it take to get within 2% of the value you actually want it to do? And again, you can look at it in terms of the scaling factor here as well. But I'm basically interested in making sure that you can, if I gave you this plot, you'd be able to draw it on there. That's the main thing, right? If we now think about a canonical system, let's think about a canonical system that we can analyse. Mass spring damper. Let's think about the differential equations of movement of a mass spring damper. We've done it loads of times, so I'll just quote it as saying it's obviously the force applied equals resistance from mass, resistance from viscosity, resistance from the spring. So x is the displacement from equilibrium, so it's going to be m d squared x dt squared plus c dx dt plus kx. And now we want to predict the response. This time, though, we're going to use an example where we're going to pull it down and let it go, so we care about initial conditions. So we have to put those in. So the d squared x dt squared, we have to put in the initial conditions when we do the Laplace of this. So it's s squared x of s, take away s x of 0. So in other words, that's s multiplied by the initial displacement, take away dx dt, which is basically take away the initial velocity, right? So that's when we start needing the fully initial conditions. So here we're going to just do dx dt goes to s x of s, take away x of 0. So that's take away again the initial displacement, and the third term is quite simple. Kx goes to k capital X of s. So we've got our initial conditions in there. And now what we're going to say is, this is what we want to analyse in this particular case, is we're going to say we're going to pull the mass down, right? We're going to pull it down. We're going to hold it still. So pulling it down means we've got an x0 of whatever we pulled it down by. We're holding it still, so it's not moving. So dx dt is going to be 0, and then we let it go. So because we let it go, there's no force on it, right? So we've got we've got three things from consideration of how we're going to start it off. We've got the initial displacement, it's going to be x0, initial displacement. It's not moving, dx dt equals 0, and f of t, which is going to be the applied force, is 0, because we're just letting it go, there's nothing perturbing it at all. So, given our equation that we came up with, we can then stick in the x of zeros, or we can stick in the dx dt, and we can get rid of the f of s as well, because that's going to be 0, right? So we've got rid of this, and we've stuck in the x of zeros here as being the initial displacement. So we just have to rearrange to factorise out x of s. And what we see now is x of s, we can write that as being x0 ms plus c divided by ms squared plus cs plus k. Right. And now this is where we start using canonical form, because I want to be able to say something about this system, and we can, like I said, if we write it in canonical form, which is a standard way of writing things, if we can get it in that form, then we can immediately say things about the system just looking at the values of the coefficients in front of the terms. Right. So we need to get rid of the m because we need unity in front of the s squared term, right? So we go through, divide everything by m, right? So that's gone from there, and it appears there and there, gone from there, appears there. And we compare with canonical form. Now, I'm not bothered about the top bit. That's not at all obvious how to get that bit, but we do care about the bottom bit. So we can see unity term there, unity term there. C divided by m has got to be equivalent to 2 zeta omega n, and k over m has got to be equivalent to omega n squared, right? Those are the two things. So we can basically we can then calculate. Yeah, so here we're just putting basically the omega in. So omega n equals square root of k over m. In fact, that should be a z. That should be there should be a zeta in there equals that bit, shouldn't there? So zeta equals, yeah, substituting everything in, we get a nice simple expression for these two things. We get an expression out for the natural frequency, and we get an expression out for the damping ratio. Now, we see that the solution to this equation, again, we've already been there. What's the characteristic equation of this system? It's when this goes to 0. Has a 0 when the top, when s equals minus 2 zeta n, zeta omega n, and it has poles when, sorry, the denominator goes to 0. And that's the equation we had previously. In this particular case, then we're going to just plot them onto the onto an argand diagram, and we can see that basically we've got one pole along the one zero along the real axis here, and we've got the two complex conjugate poles as well on this diagram here.